Welcome back. Let's move forward to our next problem, which is matrix chain multiplication. In this problem, we are given a sequence of matrices or a chain, for example 4, 3, 2, 5. That means matrices are of size 4 by 3, 3 by 2 and 2 by 5. The problem is to find out the most efficient way for multiplying matrices of these dimensions. So we don't perform the actual multiplication, we just figure out how many operations it will take to multiply matrices. Now the first way to perform multiplication could be multiplying first two matrices that will take the multiplication of 4, 3 and 2 operations that are 24, and then multiplying the result matrix to third matrix. That will take multiplication of 4, 2 and 5, that is 40 more operations. So parenthesizing first two matrices will take total 64 operations. Another way is to multiply these two matrices first, that takes 30 operations, and then multiplying the result with the first matrix. So overall this will take total 90 operations. Though multiplication is associative, that means either way we will have the resultant matrix of size 4 by 5, yet in which order we parenthesize the product affects the total number of operations required to perform the multiplication. Clearly, if we go with this way, we need to perform less number of operations, so this is the most efficient way. So in problem, we will have some sequence of suppose n numbers. That means we will be having n minus 1 matrices. Here the size of every ith matrix is the value present at I minus 1th index and ith index. Like for matrix A1, the size will be 40 by 30. For A2, it will be 30 by 10 and so on. So we need to find minimum operations to multiply all these matrices. Now let's think of the solution. Suppose we have 4 matrices. Now first way to put parentheses after matrix A1, that is multiplying result of A2, A3, A4 with A1. Now for multiplying A2, A3, A4, there are two ways: multiplying A2 with A3, A4, or first multiplying A2, A3 and then to A4. And to multiply A3, A4, there is just one way, as well as for A2, A3 we have one way. So that's the first way for multiplying A1, A2, A3, A4. We can also put parentheses here and multiply A1, A2 and A3, A4 first, then multiply their resultant matrices. Or we can multiply first 3 matrices first and then multiply it with A4. Here again we check every possible order in which we can perform multiplication. That's how we're gonna divide this problem into subproblems. We start from I and go till j and check for each position k where we can place the bar. We compute operations in every case and go with the one which is minimum. Like first we place the bar at 1 and we check for both the sides. In left, that is whereas I is equals to k, there's just one matrix, and in right side we start from k plus 1 and check till j. In the same way we place the bar at 2 and divide it into two subproblems where first starts from I to k and second from k plus 1 to j. Similarly, the third one where we place the bar after third matrix, that means we multiply first 3 matrices first and then the last A4. Now we compute the number of operations for each subproblem. If at any side there is just one matrix, then no operation will be required for that subproblem. And for other subproblems, we need to recur and compute operations for left side of the bar, that is from I to k, and for right side of the bar, that is from k plus 1 to j, and then the number of operations required to multiply the resulting matrices, and we take dimensions for them from the given sequence, which will be present at index I minus 1, k and j. For instance, for this sequence we have three matrices. Here k is at index 2, I at 1 and j at 3. So the number of operations in combining the resulting matrix and this third matrix would be the value present at I minus 1 index multiplied by value at k and value at j index. As this first resulting matrix will be of size 4 by 2, that are the value present at I minus 1 index and kth index, and the second matrix is of 2 by 5, which are the value present at k index and j index. So let's see the recurrence relation. To compute minimum number of operation for sequences of matrix starting from I to j, we divide it into two sequences with k and recursively compute minimum operations for sequence I to k and from k plus 1 to j. And we calculate operation required to multiply the resulting matrices. The total number of operation will be the addition of all these operations, and we choose the minimum among all possible ways. Here k, from where we split the sequence, is in range from I to j, and the base case is when there is a single matrix. That means if I is equals to j, then number of operations will be 0. This is the recursion tree for matrix chain 4. You can say this is having similar subproblems. MCM 3-4 is called twice, MCM 2-3, MCM 1-2 and many more subproblems are computed more than once. So this problem can be solved with dynamic programming, where we use array to store the result of all subproblems. Let's do that. First way to memoizing the results in top-down approach. We build a two-dimensional array as we have two variants in recurrence, which were I and j. Now this matrix will be of size n by n, where each cell represents a subproblem. Like cell 2, 3, this cell will have result of the subproblem 2, 3. That means when we compute number of operations for a to a3 multiplication, we will store it to this cell. We fill this array with -1 initially, and for the base case, when I is equals to j, we put 0 at these diagonal indices. And we continue to fill array while solving every problem recursively. The final result, which will be for multiplication for all four matrices, will be stored at location 1, 4. As I is 1 and j is 4 here. So we return value present at this index. Let's try the bottom-up approach, where we start filling the table from smaller subproblems first. We create an array of n by n to store minimum number of operations for each subproblem. We know if we want to get minimum number of operations for these four matrices A1, A2, A3, A4, we have to know the result for all these smaller subproblems, which are of chain length 3, 2 and 1. So the main focus would be length while we implement this approach. We start filling the table for smaller length of sequences. We know if there is single matrix, the number of operations will be 0. So in this array, we put 0 at cells 1, 1, 2, 2, 3, 3 and 4, 4. Now to solve other subproblems, logic is same. We will put k at different indices between I to j and calculate minimum number of operations for every sequence. Now to get those different length sequences, how do we locate ij pointers? Let's understand that. Starting from two length sequence, if I is at index 1, our j should be at index 2. So that will be a two length sequence. Similarly, if I is 2, then j should be 3. So 1, 2, 2, 3 and 3, 4, these will be all two-length sequences. We put K and split them into 1, 1 matrix, and we know their answers. We add 0, 0 and the number of operation to multiply A1, A2, that will be multiplication of 4, 3 and 2, which is 24. So at index 1, 2, we place 24. In the same way, we filled values for 2, 3 and 3, 4. Next, we move 3 length sequences. Again, I starts from 1, J will be at 3. We start to place K from I. K at 1, we split it into A1 and A2, A3. We have answers for these two. For A1, it's 0, and for A2, A3, it's at index 2, 3, which is 6. And we add number of operations to perform multiplication of the resulting matrices of size 3, 1. So logic is same. We multiply value at I minus 1, K and J. So it will be multiplication of 4, 3 and 1, which will be 12. So total operations in this case will be 18. Now we change K to check if with the next option we can get operations less than 18. So left sequence is A1, A2. For A1, A2, value is at 1, 2 position, which is 24, and for A3 it's 0, and number of operations to multiply these will be multiplication of 4, 2 and 1, that's 8. So total operations in this case will be 32. So among these, 18 is the minimum, so at index 1, 3, we update 18. That simply indicates for matrix chain 1 to 3, the minimum number of operations will be 18. So we are having result of smaller subproblems with us to compute the bigger one. So next sequence would be A2, A3, A4 when I is at 2 and J will be at 4. And we calculate operations when K is at 2 and 3. And update the minimum value at index 2, 4, that is 21. Now the last problem is of length 4. We just have one problem of length 4. So when K is at 1, we need to perform 81 operations. And when K is 2, that's when we multiply result of A1, A2 and A3, A4, we need to perform 74 operations. And when K is 3, we just need to perform 38 operations, which is the answer. So while implementing this approach, we solve smaller length sequences first. We go through every length and set our ij pointers. For each length, pointer I will start from 1 and go till n minus length. Like if length is 3, I can move till index 2 only. As if it goes beyond 2, it won't find sequence of length 3. And if we need to fix j as well, when I is 1 for length 3, j would be I plus length minus 1, that's 1 plus 3 minus 1, that will be 3. Or for length 2, if I is at 2, then j will be at 2 plus 2 minus 1, that's 3. And then we simply put k in range from I to j to compute minimum number of operations for multiplying matrices. At last, we get minimum number of operations at nth column of the first row. Hope you got the logic.